This program is presented by University of California Television. Like what you learn? Visit our website or follow us on Facebook and Twitter to keep up with the latest UCTV programs.
Funding for this program was provided by the UCLA Office of Instructional Development.
Good afternoon. It is my pleasure to participate in UCLA's 115th Faculty Research Lecture by introducing our colleague, Professor Richard B. Kaner, Distinguished Professor of Chemistry and Biochemistry and of Materials Science and Engineering, as you see. Professor Kaner received his PhD in organic chemistry from the University of Pennsylvania in 1984 and conducted his postdoctoral research at UC Berkeley before joining UCLA's faculty in 1987. He is the recipient of numerous awards, including the UCLA Gold Shield Faculty Prize, the Luckman Distinguished Teaching Award, the American Chemical Society Buck Whitney Research Award, the National Science Foundation Presidential Young Investigator, the American Chemical Society Tolman Medal in Chemistry of Materials Award, the Guggenheim, Sloan, and Packard Fellowships, and but we'll leave some room for him to talk. You could see I could go on and on. Professor Kaner's work has resulted in over 275 research papers, and he now holds 14 US patents with 20 more patents pending. Throughout his career, Professor Kaner, or Rick, has been known for the access, inclusiveness, and mentorship he provides for both undergraduate and graduate students. He has inspired generations of students to use knowledge and discovery to change the world by changing people's lives just as he has. His research has been described as encompassing the intriguing elements of power, strength, and flexibility in a way that will impact the future. Today's lecture is entitled The Quest for New Materials, Superhard Metals, Conducting Polymers, and Graphene. Please join me in welcoming our 115th Faculty Research Lecturer, the distinguished colleague, Professor Richard B. Kaner.
Thank you. It's a great honor and pleasure to be here, and when you look at the list of previous winners, it's a rather humbling experience. Today, I want to tell you about some of our work on new materials. And this I look at as an opportunity to thank my students and my colleagues and some of my predecessors for making this possible. And what I want to do, is start with the slideshow. And let's try this again. So my journey began as an undergraduate at Brown University when I was bored in freshman chemistry, talked to the chair, and found out that I actually probably shouldn't be in freshman chemistry. So then I said, well, I'd like to do research. So right at the beginning of my first semester as a freshman, I walked into this person's office, Professor Aaron Wold. And I said, I'm interested in doing research. And he said, well, I have a project for you. So he said, I need you to grow some crystals. 6 weeks later, I ran into him, and he said, any luck? I said, yeah. And he came and looked, and he was so impressed that he hired me, and I spent 4 years working in his lab. I found out later that he had given the same project to a graduate student and who didn't actually succeed. So in Aaron Wold's lab, I learned the art of solid-state chemistry. I also had the pleasure a year and a half ago of being invited back to Brown University, and although he's retired, he came to my lecture. It was great fun. Well, I learned about how to make materials at high temperature using solid-state reactions. And I had this idea when I came here that we develop low-temperature reactions. So I'm going to show you one of our low-temperature reactions. It's called a metathesis reaction, where we take A, B, and CD and recombine them. So you can judge for yourself if this is actually a room temperature reaction. This is in a vessel under helium. And what we're doing is we're taking aluminum pentachloride and sodium sulfide. And you'll see this again. And we just mix them together, and we wait about 30 seconds. And I'm showing you after the 30 seconds. And you can see the reaction takes off. This reaction was to make some molybdenum disulfide, which is actually the world's best lubricant. You can see this appeared on the cover of Nature. And this is in our dry box under helium. So this is technically a room temperature reaction. It just happens to get to 1400 degrees within a fraction of a second. We've gone on to make over 100 materials by this process. And you can see here we're making the ceramic zirconium nitride. And this is a few frames taken a half second apart. We can also make materials under high pressure. And if you look here, we're making tantalum nitride. And we borrowed a press from my colleague, Mal Nickel, and we ran this reaction at 45,000 atmospheres of pressure. And we just set it off, and we were able to make this phase that had only been made before under high pressure. So one of the things I like about UCLA is the excellent colleagues. And one day I got a call, and it was from Jack Gilman. And Jack said, you probably don't know me, but I'm a professor in material science. I do theory. And I was reading one of your papers on making high-temperature borides. And I was wondering if you ever thought about making super hard materials. And I said, well, I've actually worked on some new forms of diamond. And he said, great, we need to talk. And he showed me this chart that showed that osmium was the most incompressible transition metal. It was almost as incompressible as carbon in the diamond form. And so it became obvious that if we could combine osmium and boron, we could make a very incompressible material. Well, here's incompressibility known as bulk modulus. And when we made osmium diboride using metathesis reactions, we found out that it's one of the most incompressible materials that have been made. Here's diamond, here's the next cubic boron nitride, here's all sorts of very hard materials. Now, hardness is, you must have something that's incompressible, but it's not a sufficient condition. So the idea was we're going to put in short covalent bonds to get this to work. When we do this, if you look, this is a hardness versus applied load, and it's quite a hard material. In fact, it scratches sapphire. This is scratches we put in a sapphire window. Sapphire is 9 on the Mohs hardness scale. So we realized we're on to something very interesting. Of course, nobody really cares if you can scratch sapphire, but the question is, could you make this harder and could you scratch diamond? And we did that by switching to rhenium. And when we did this, here's a scratch put in diamond by rhenium diboride, and you can see just how hard this is. After we did this, and I should point out that this is work with my colleagues Abby Kavner from Earth and Space Sciences, Jimin Yang from Materials Science, and Sarah Tolbert, who I've been working with for years. She's an expert in measuring compressibility. And after we did this, I got a letter back a couple months later from somebody who didn't believe that we could actually have scratched a diamond. And they challenged us to show the gouge put in a diamond. Well, of course, the student who had done this had gone. And I asked another student who came back a couple hours later and said, well, this doesn't seem to work. So I said, well, just take 2 diamonds and scratch one diamond against the other. And came back an hour later and said, well, that doesn't seem to work either. So we discussed it, and we figured out that it has an angular dependence. And if you get the right angle, you can take our rhenium diboride and put multiple scratches in diamond. So we put another scratch in diamond, and we sent it back, and reviewers decided this was really interesting. So here's another paper that appeared in Science. And this is the diamond surface as measured using atomic force microscopy. And you can see the gouge, and here's the profile. You can see we put a nice scratch in the diamond. And then we analyzed the surface to make sure that it was all carbon. And you can see the pixels for carbon, and you can see there's no pixels for rhenium. So we really did put a scratch in diamond. Well, they sent it to reviewers, and they got a chance to change their comment before it was published. And so they said, well, we didn't believe you could scratch diamond, but it doesn't matter because rhenium's too expensive to be of any practical value. Of course, we got to change our answer, and we said, well, you told us that we couldn't scratch diamond, but we did. Here's the proof of it. And in fact, you know, it's a science project, so it doesn't really matter. But in fact, it does matter. I mean, I really, when I'm looking at making new materials, I want something that will actually be useful. And so this was a real problem. And so what we decided to do is find a metal that was less expensive. And we came up with tungsten tetraboride. And what I want to show you here is this is electric discharge machining. You may ask, why would you want a hard metal? And the reason you want a hard metal is, unlike diamond, which can only be cut with other diamonds, is you can cut it with an electric wire. This is an electric wire underwater, and you can slice through a metal like butter. So you could make a really hard metal, you could cut it, and then you could use it to cut and polish other materials. And so if we look at this next slide, This is an ingot of tungsten tetraboride. And tungsten is not a particularly expensive metal. And so this is how we make the materials. And then we took a slice through this using an electric discharge machine. You can see we cut this out, and we make cutting tools. And this is what we're doing now. And we're hoping that this will actually one day be practical. In fact, my student, Chris Turner, who did this, he made an ingot here, cut it out, and then on a lathe simply turned a piece of aluminum, which is not an easy thing to do. And so the goal is that we can make a material that is much harder than currently used cutting materials and use it for cutting, polishing, and protective coatings. Okay, I'm going to change gears to my next subject, which is conducting polymers. And this is something that I learned in graduate school from this gentleman, Professor Alan McDermott. And I went to the University of Pennsylvania because a friend of mine told me that they had just made this great discovery and I needed to get myself there. And what they had discovered is the first conducting plastic. And here it is, cis polyacetylene, and here's the transform, and here's aluminum foil. And you can see, either we're bad at taking pictures or this material looks metallic. Well, it's not actually metallic. In order for something to be metallic, you have to have two conditions. One is you have to have a pathway for electrons or charge carriers to move. And the other thing is you need those charge carriers. So here's the structure of polyacetylene. You can see alternating double and single bonds. And that conjugated system provides the pathway. However, you have to dope it to provide the electrons or the holes. And in this case, this is iodine in the form of I3-. It pulls an electron away, and there's holes that run along these chains. And this is the first conducting polymer, and it led a number of years later, 20 years later, to the Nobel Prize for Alan McDermott. And I was invited back to the University of Pennsylvania for a Nobel Prize symposium. And I said at the time, we had a joke that he had probably never heard, a joke from graduate school. And the joke is, what is the only true application for polyacetylene? Now you have to understand that this material is air sensitive, so everything was done in the absence of air. And the answer to the joke is to produce PhDs. But I said on this occasion, we now know it's a dual-use material. So PhDs and Nobel Prizes. Okay, so we don't work on that. Almost no one in the world does. What we work on these days is something called polyaniline. And aniline is a very inexpensive material. In fact, if you're wearing any blue, green, or black clothing, they're aniline dyes. And they go back 150 years. And then one day, one of my colleagues invited Bruce Weiler from Aerospace Corporation to give a lecture. Aerospace Corporation is near LAX. It's basically a national lab. It has 1,400 PhD scientists, and they work on Air Force projects. And in their spare time, they can do what they want. So Bruce came, and he put up this picture of a shuttle going up. And he said that one of the things the Air Force wants to know is what happens to these plumes. And the reason they want to know is people keep living closer and closer to launch sites. And so we talked about the cheapest sensors, a resistive type sensor. And he said, the plumes, there's ammonium perchlorate that is burned, and one of the byproducts is HCl, hydrochloric acid. So if you could detect hydrochloric acid, you have a really good detection system. Well, I told him we have this conjugated polymer, and it's in an insulator, 10 to minus 10 Siemens per centimeter. But if it seeds hydrochloric acid, it has over 10 orders of magnitude change in conductivity, which is just absolutely huge. So he's like, great, send me some. So I sent him some, and 3 weeks later he called me and said, well, I got good news and bad news. So I said, well, start with the good news. He said, well, the good news is it works. I said, well, then what's the bad news? He said, well, it's slow. So I met with my research group, and one of my graduate students said, don't worry, I'll make some nanoform of the material, and we can speed up this reaction. And so what we did is we did an interfacial polymerization. This is, you can make nylon by this method. But basically, we took aniline, this cheap starting material that comes from coal. We put it in an organic solvent. We took oxidizing agent and acid, put it here. And 30 seconds later at the interface, you can see the conducting polymer forming. Why can you see it? Because it's conjugated, and therefore it absorbs visible light. So as soon as you see it, it's forming. Now, this is a minute, 2 minutes, and 3 minutes. You'll notice that as it forms, it goes into the water phase. And that's because it forms in the doped salt form. And so it disperses in water. And we particularly chose a more dense organic phase so that gravity has nothing to do with it. And we looked under microscopes, and we have some really good microscopes in our Nano Institute. What we see is, by transmission electron microscope, that nanofibers that are about a micron in length and 30 nanometers in diameter. And if we change the acid, HCl is 30 nanometers, camphor sulfonic acid about 50 nanometer diameter fibers, and hydrochloric acid about 120 nanometer fibers. We then looked at how everybody else had been making polyaniline. And what they did is they put in 1 drop of acid into aniline. And when we repeated this experiment, what we did with a stop flow reactor, we found the first drop actually produces nanofibers. And it's the next thing that produces agglomerates, and eventually you get this agglomerated form of the polymer that doesn't disperse and isn't useful. In fact, one of the things that I learned in graduate school is the only reason that conducting polymers haven't been used for very much is, unlike conventional polymers, they don't melt and they don't dissolve. However, after we did this, we realized that we could make our nanofibers disperse in water. And in fact, I'll even show you we now know how to melt them. We discovered that process too. But it led to this much simpler process. And the idea is if we take oxide and aniline and throw them together in a stoichiometric amount at room temperature, we use up all the aniline, form nanofibers, they can't agglomerate. And so this process makes nanofibers in as large amount as you want. And I can say that because we worked with Korean nylon, known as Kolon, and they scaled up our reaction with our help to a 100-liter pilot plant reaction. And so you can do this and you can make as much of this material as you want. Now, we've also looked at coating technologies, and one of my students, Julio Darcy, invented a coating material that, if you think of making salad dressing, you take oil and vinegar or oil and water and put it together and shake it. Of course, it tries to separate, and it forms a catenoid. And so what we did is we took our nanofibers of the conducting polymer, we put it in that oil-water mixture, and as the catenoid breaks up, it sends a film growing up the side, the wall of a tube. And if you put a glass slide in, you can make all different colors. So here's polythiophene in red, and doped polyaniline in green, and de-doped polyaniline blue. So we can make coating technologies. In fact, he earned the silver medal in the National Collegiate Inventor Hall of Fame competition for this discovery. Okay, getting back to sensors. So Bruce and I looked at the sensor activity, and here's the change in resistance on a log scale versus time. Here's the conventional material. It sees an acid, and the resistance drops. Here's the nanomaterial. It drops 6 orders of magnitude greater. And so we thought we had a really interesting sensor type material. And the reason it does this can be seen if you look, here's a conventional material. And when the acid comes in, of course, it dopes the surface, but in order for the conductivity to get through, you have to diffuse the dopant and it's got to send the signal. On the other hand, here's our nanomaterial on an electrode surface. Of course, in this case, there's no diffusion barrier, so the gas can come in, and as soon as it hits one of these surfaces, it sends an electrical signal, and we get a very instantaneous response. And you can see this, you can do it with acid in the de-doped form, or you can take the doped form and bring up base. Here we're bringing up ammonia, we turn it on, the resistance goes up, we turn it off, and it's reversible. And this we're doing less than 1 part per million of ammonia. Now, you know your nose is very sensitive to ammonia, but even the best nose cuts out at about 25 parts per million in air. So this is, you could not smell this. So one of my students said, well, I can just go over to Radio Shack and, for a couple dollars, I can build a neat little sensor and we can do a demonstration. Okay, so here is what we did. And for $1, we got an LED and a comparator circuit. And then Aerospace provided this interdigitated gold electrode, but we didn't pay for it, so thank you, Bruce. Okay, here's Zhejiang Wang. This is 1 part per million of ammonia. Watch the LED. It takes about 2 seconds, and you'll see it detects that. He's going to pull it out, and it will reverse itself. And then he's going to do it 1 more time. And of course, if you put your nose in this, you'd smell nothing, because it's just 1 part per million of ammonia. But the detector is very sensitive. So we can go on and we can do detection. Now, one of the things I like is we can actually do this in a very interesting way. And so we decided that this is such a straightforward experiment that we could teach our graduate students to do this. So we introduced this in Chem 285, a graduate student course. And this is from the Chemical and Engineering Trade magazine. This is one of our graduate students looking at an oscilloscope. In fact, we wrote this up for the Journal of Chemical Education, and we started teaching this to high school teachers. And so Sarah Tolbert runs this program in the California Nanosystems Institute, in which 25 high school teachers come in on a Saturday. And we do this every couple months. And so I go over and I'll give the lecture, and then the students will work with the teachers and show them how to sense things. And then we give them kits, and they go back to their high school classrooms. And so hundreds of students across LA high schools have now done this experiment where they take these polyaniline nanofibers and they expose them to things like lemon juice and vinegar, any household acids and bases, and it's a really wonderful experiment. Okay, these nanofibers, we can do many other things. Here's gold particles on them. You can see 10 nanometers. So these are about 1 nanometer gold particles. And once you put on gold, you can do all sorts of other things. So we built memory devices. This is work with Yang Yang and Fraser Stoddard. And you can see our crossbar memory devices here. You can see this article about all different types of memory. We can also put palladium nanoparticles, and I was asked to do this by my colleague Paula Diaconescu, and she's an expert in catalysis. And what she was interested in doing is a coupling reaction called Suzuki coupling. Suzuki won the Nobel Prize in Chemistry in 2010, and he shared it with Richard Hecht, who was an undergrad and grad student in our department. He's come back since. And these coupling reactions are simply taking things like boronic acid and aryl chloride and putting them together. Well, it turns out that polyaniline nanofibers are a great platform for the palladium, which can run these reactions under very mild conditions. Now, I promised that we could actually melt this polymer. And here's how we do it. We took the polymer and we exposed it to a camera flash at close range, and it melts. And this is a very interesting phenomenon. So it absorbs the light, converts it to heat, and it happens so fast that it melts. You can't melt the polymer by heating it, it simply cross-links. But you can do patterning with this. So this is a copper transmission electron microscope grid, and this is the doped form of the polymer. It doesn't matter if it's doped or de-doped. But we like this because of the color contrast. So we hit this with a flash of light, and we remove the grid. Where the grid protected, it's still green and nano. Where the grid didn't protect it, it actually melted. And you can see the huge contrast. These are real colors. Now, you can do real patterning with this. And so here's a patterning done with a laser scribe device, just taking a 780 nanometer laser. It's a $25 device, and I'll tell you more about this later. And we can write on CDs, we can write interdigitate electrodes, we can make sensors, we can write UCLA. I had the opportunity to spend a sabbatical in Australia with Gordon Wallace on a Fulbright fellowship. And what we did is we took this material and we simply melted the top surface. So this is looking at a cross-section. So you can see here's the nano part, here's the melted part. And we use this for an actuator. So we dip this in acid. The nano part absorbs the acid and expands. The melted part cannot expand. So if you think of your hand as an actuator and you were to dip it in acid, it will curl up. And this thing in 20 seconds will do 2 full rotations. We stick it in base and it uncurls. So you can make the motion of a human hand or an actuator. Now, I said this was in Australia. I want to prove that. So here's a picture we took in Australia. This is my family who are here. This is a few years ago. And by the way, that koala and the eucalyptus leaf, that's in his mouth, not my mouth. And if you want to hear more about this, this is one of our pieces of polyaniline that's been hit with a laser. And it's very hard to tell the difference between the welded side and the non-welded side unless you look under a high-powered microscope. But here's the microscope images. This is false colored. And here's another article in Advanced Materials in which we describe the nanofibers. I'll point out that we actually wanted to understand the basics of these long polymer chains. And to do that, we looked at the tetramer, which is the smallest repeat unit. And in this work, we made some very nice structures. And we looked at the conductivity. And the way we did this, we went to my colleague Zhongfeng Duan, and he has the ability to put these between 2 gold electrodes. Here's a little tiny nanowire. And we measured it, and it's metallic. And so this 4-unit long segment has a conductivity almost as good as the bulk material, which is 1 to 10. It's over 1. And so this is remarkable. And it means that the electrons in this material can hop very nicely from one place to the other if you align it perfectly. In fact, this material is so well aligned. We did this with Chris Regan in physics. We were able to get single crystals of this. And I just want to show you one single crystal. And so Jessica Wang last year entered this in the Materials Research Society Sciences Art Contest. And this is a single crystal of polyaniline. Well, it's actually multiple single crystals. The only thing that's false colored, we colored this violet, and we called this tetraaniline in full bloom. And she won first prize in this. All right, let me turn to my third subject here. So the third thing, and for this I want to thank my postdoctoral advisor from the institution to the north. And Neil Bartlett, when I went to work in his lab, we worked on graphite. And my postdoctoral project was to develop new forms of graphite. And in it, he talked about a dream that he had with graphite. And the dream was someday to make a material that had a high surface area. He called it holy graphite. So if you think of all the batteries you use, one of the electrodes, and sometimes both, are graphite-based electrodes. And graphite it's a very cheap material. You can mine it. It's highly conductive. But it has one drawback. It has low surface area. And so he had this dream of making holy graphite, spelled H-O-L-E-Y. And I'll get to that in a little bit. This is one of my favorite pictures of graphite. This is called highly oriented pyrolytic graphite. And what we're doing here is hitting it with a laser. A normal material, when hit with a laser, gets hot in 3 dimensions. But graphite is not a normal material. It's a 2-dimensional material. And heat, or thermal conductivity, follows 2 pathways. It follows the chemical bonds, known as the phonon modes, which are in this direction, because it's all the bonding's that way. And it follows the conduction electrons. And again, the pi star orbitals overlap, and they overlap in that direction. So all the heat transfers in 2 dimensions. So if you touch here, you burn yourself. If you touch here, it's cold. And this is the only picture I've ever seen of a property, atomic scale property in 3 dimensions. Okay, well, enter the world of graphene. Graphene is a very interesting material. It was discovered in 2004. Novosel and Guggenheim, who discovered it by peeling that stuff with Scotch tape, won the Nobel Prize in 2010. And you can think of graphene, a single layer of graphite, as a building block for all other forms of carbon. So for example, if you put 12 5-membered rings in, you get something called fullerenes, named after Buckminster Fuller, who invented the geodesic dome. You can roll up a sheet of graphene and you can get something called carbon nanotubes. Or you can stack it up and get graphite. But of course, these forms were discovered much earlier. These 2 basically in the last 25 years. Now, our work in carbon dates from the earliest time I was at UCLA. And this is work with my former colleagues, Francois Diederich and Rob Wetton. And what they did is they came up with a large amount of carbon-60. And Bell Labs had just discovered conductivity and superconductivity in it, but they had a very small volume fraction. They had about 1%. We made the first pure samples and got the structure. And the structure is here, and you can see that here's carbon-60 and here's potassium. And they sit on all octahedral and tetrahedral sites. And this, you know, I have a nice model in my office made out of soccer balls. In fact, I can probably tell you this story. I walked in order to make this model, you need 14 soccer balls. So I was in Toys R Us, and I had my cart filled with 14 soccer balls. And the guy in front of me kept turning around, and he said, "Can I ask you a question?" And I'm like, "Sure." He said, "Are you the coach of a Little League soccer team?" And I said, "No, I'm actually doing a science project." What I didn't tell him is that I was a professor at UCLA and that I was using taxpayer money to buy soccer balls. But anyway, so we looked at this. We then went on, and here's how Novosel and Guggenheim won the Nobel Prize, by taking Scotch tape and peeling it. And they kept peeling until they got down to a single layer, which is just quite remarkable. But there's other ways of making graphene. One is by chemical vapor deposition on copper, and a number of people have done that. And then if graphene's ever going to be useful, you need a method that you can scale up. And so we're interested in doing solution processing methods. In fact, one of the things I really like about UCLA, as I said, is we have wonderful colleagues. So in the year 2000, this is 4 years before graphene was discovered, Tom Hahn knocked at my door. Tom Hahn's a professor in mechanical engineering. And he said, "I understand that you're a resident expert in carbon." And I said, "Well, I've been working on carbon for a long time." He said, "Good. I need you to make me a single layer of carbon. Can you do it?" And I said, "Well, probably, but why would you want it?" He said, "Well, I did the following calculations, and a single layer of carbon would be the best reinforcement for polymers." And then he's like, "Well, how would you do it?" I said, "Well, graphite's a layered compound. It's been known for many years that if you heat it in the presence of potassium, it forms what's called a first stage intercalation compound. Between every layer of carbon, you get a layer of potassium plus. And it's a nice gold-colored compound." And I said, we'd then take the compound, we'd hit it with water or alcohol and blow the layers apart. He's like, "That's great, you got to do this." So we did this, and then we sonicated it. And interestingly enough, these things scroll up. And so here's a carbon nanoscroll. This is a lacy carbon grid behind it, but you can see this nice scroll. And here's a more tightly round scroll, and here's a whole lot of scrolls. Now, what's interesting is this is a paper we published in Science in 2003. So this is 1 year before graphene was discovered. But our goal was to make graphene. And so I actually took out a patent in 2002 on graphene. And so the patent hasn't been licensed, but I'm very hopeful that graphene will be useful and this patent will someday be recognized. Okay. After Lucile and Guggenheim did their work, we realized that the only problem with our method is it not only makes one layer, as people have subsequently shown, but it can make 2, 30, all different numbers of layers. So we switched our research a little, and we started looking at graphite oxide, which is if you oxidize graphite in water, you can divide it into individual layers that are oxidized, and then you have to get them back to graphene. And from this graphite oxide, we've made everything from graphene paper to electronic devices. We've worked with Kang Wang in electrical engineering. We've built sensors. We've done foam. We've done light scribe and supercapacitors. And I'll show you this because supercapacitors are really interesting. You know, if you could solve the energy storage problem, that would be very helpful. And this may be part of a solution. Okay, first just a word about graphite oxide. So here's a layer of graphite that's been oxidized, disperses in water, and this chemistry goes back over 150 years. Well, when we picked it up, we looked anew at graphite oxide, and we find that when you reduce it with hydrazine, a good reducing agent, it forms a dispersion in water. I say it's a dispersion because if you look at the laser light going through, if it's a solution, the light goes through. But if it's a dispersion of nanoparticles, the light bounces off. So we have all these little particles, these little sheets of graphene, and they stay apart because every sheet is negatively charged. They don't like each other. Now, it's called a charge-stabilized colloid because if we add salt, the salt neutralizes the charge and they all flocculate out. You can see that here. And if you look by atomic force microscope, here's individual sheets of graphene. And if you run a probe along, you can see this going over. It's about 1 nanometer step height, and you can show that it's graphene. Well, this is an article that we did for Nature Nanotechnology with my collaborator, Gordon Wallace. And last year, the editor-in-chief sent me an email telling us we had the most highly cited paper in the history of their journal. And so today it has over 2,800 citations. Okay, we can scale this up. We can make as much as you want. So we take this reduced graphite oxide, this chemically produced graphene, and we run it through filter paper, and we just peel it off plastic filter paper. And so this is graphene paper. And it's a little bit different than graphite. Graphite's AB stack. This is just random stacks of many sheets of graphene. And you can see it's very highly reflective. We even tried reducing this in pure hydrazine to make an even better colloid and a better material. And this is work done with Yang in material science. And when we did this, at the time we produced the largest sheets of graphene that had been made. And this is a scanning electron microscope picture of a very large sheet of graphene. And here's an atomic force microscope picture. And I think if you stare at these for a moment, you'll agree that these are the same picture. So about 20 by 30 microns. And I was getting support at the time from the Defense Advanced Project Research Agency. And we were having a meeting at UCLA. We had about 25 people. And the program manager looked at this slide and he said, well, Rick, this is nice, but there's a problem. I'm like, what's the problem? He's like, something's missing. I'm like, what's missing? He said, Florida, it's missing. Yes. So we decided that program managers actually have a sense of humor too. So we ran an atomic force microscope probe across white, red, and blue. And what you'll see is the step height is about 0.6 nanometers. And by doing this, we could demonstrate that this really was a single layer of carbon. Okay, well, what can you do with a single layer of carbon? Well, with Yang, the best transparent conductor is known as indium tin oxide. So all your cell phones and your flat screen TVs all have a coating of indium tin oxide. But it's not very flexible. How do we know that? Well, we took indium tin oxide on plastic, which is polyethylene terephthalate, like Coke bottle, like this kind of plastic. And we took our graphene and we mixed it with carbon nanotubes. And we made a material that's equally conductive. Then we bent them each 10 times. Well, the indium tin oxide is a nice crystalline inorganic solid, and you bend it 10 times, the conductivity drops by a factor of 1,000. When you bend our carbon nanotubes and our graphene, nothing happens. And so you can actually make flexible electronics out of this. And many companies are now looking at thin sheets of carbon for electronics. And you'll start seeing flexible cell phones, other flexible electronic devices. You can also make sensors, and this is working with Bruce Weiler again. And we looked at the detection of 2,4-dinitrotoluene at 52 parts per billion. Now you may say, why do I care about that? Well, the cousin this of dinitrotoluene is trinitrotoluene, or TNT. And so this is the volatile component, and it has a vapor pressure above 700 parts per billion. And so if you can detect this, you can use graphene to detect explosives. Okay, another thing you can do with this material, this is freeze-dried graphite oxide. And I'm just going to light this on fire to see what happens. And here we go. And I'm sure many of you played with snakes on the 4th of July. It doesn't, but what's interesting is it looks like it's burning, but it's all still there. So what it's doing is it's getting hot, it's giving off CO2, but most of the carbon's still there. Now what we're going to do is hit it with a flash of light. This is graphite oxide paper from a camera flash. Okay, so what's it doing? Again, it's absorbing the light, converting it to heat, and blowing off carbon dioxide. Completely uncontrolled reaction, but imagine controlling this reaction. So to do that, we again use LightScribe. And LightScribe is this $25 device, and we hit it with a 780 nanometer laser, and we can draw whatever pattern we want. So we paid an artist for this picture of a person with a computer for a brain, and we just told the computer to raster that image, and we reproduce that in graphene. And so where you see the light part, that's graphite oxide. It's an insulator. The dark part has been converted with a laser to graphene, and the things in between are partially converted. And we can show that we go from an insulating graphite oxide to a conducting graphene. Okay. Now, this gets really interesting. One of my students, Mahir Katie, came to me, and he started looking at the electrochemistry of this. And he came to me and he said, I measured, the cyclic voltammetry of a iron 3, iron 2 couple, and it has a peak separation of 0.059 volts. Now, I realize that that doesn't mean much to most of you, but it meant something to me. I said, well, I studied electrochemistry probably 30 years ago, and I don't think you can get that because the theoretical limit, according to the Nernst equation, is 0.059 volts. And he came back to me and he said, no, you're not quite right. He said, actually, the Nernst equation is 0.05916 volts, and I measured 0.0595 volts. So it's actually a legitimate measurement, but it says that electron transfer on a single sheet of graphene is extremely fast. And in fact, when he did the calculations, moving charge on graphene is at the rate of 10 to the minus 2 centimeters per second. And it's 100 times faster than graphite. So at that point, we realized we had a really good electrode material, and we needed to start making use of it. And so we used LaserScribe, and instead of drawing a pretty picture, we just told it to darken the whole thing. And so here's LaserScribe graphene versus the graphite oxide. And you can see the graphite oxide is this beautiful layered material. We hit it with a laser, it absorbs the light, converts it to heat, and blows off CO2. And as the CO2 leaves, it leaves pockets behind. And so here is a material, it has a fractal geometry in which it's highly conductive, but what we've really done is made a 3-dimensional corrugated cardboard network. So we have a high surface area and high conductivity. That's exactly what you want for electrodes. In fact, I wish Neil Bartlett were still alive today, because this is the holy graphite that he talked about back in the 1980s. And so it was obvious to us that we should start building electrochemical devices. And so Mahir started building supercapacitors. And here's what it looks like. It looks like a battery, 2 electrodes and a separating electrolyte, but now we're going to charge 1 positive and 1 negative. And there's no real movement of ions. They just jump on the surface and jump off. And so you can charge and discharge these devices millions of times, literally. And they can store, they're very high power. They're not quite as high energy as batteries, but they can be used for a lot of things. And this is called a cyclic voltammetry. And in theory, if you get a rectangular wave, that would be a perfect result. And this is as close as you'll probably ever see to a rectangular wave. When we compare this to commercial devices based on activated carbon, as you drive an activated carbon device faster and faster, it falls off. Our material still keeps performing. And this is up at 4,000 milliamps per cubic centimeter, very high current. We can even bend our material. This is the cyclic voltammogram as a function of bending angle. And you'll see every one of these are on top of each other. So you can now start thinking about flexible charge storage devices. And then you may say, well, you know, if I look at my computer battery, it doesn't run on 1 volt or 3 volts, but it runs at 14.4 volts. So how am I going to get there? Well, you can combine these devices in series. So here's a 1 volt aqueous cell. We put 4 of them together in series. You get out 4 volts. Here's 2 in series. We double the voltage. And 2 in parallel, we double the area under the curve. And so you can stack these together very nicely, and you can actually run real-world devices with this. And here's what a Ragone plot looks like. This is power density versus energy density. And these are what are called commercial supercapacitors. So supercapacitors bridge that of capacitors, which are high-powered devices, but they don't store much energy, and batteries, which are relatively low-powered devices, but they store a lot of energy. So the goal is to make better supercapacitors, and then we could have electric vehicles and all sorts of other good things. Well, here's our aqueous cells, here's our organic cells, and here's some ionic liquid cells. So our materials actually show they have power comparable to capacitors, and they have energy density now comparable to lead-acid batteries. And we have plans on how to make them eventually comparable to lithium-ion batteries. Okay. With that, what I want to show you now is a movie that will describe this, and it was made for the Sundance Film Festival.
A lot of times, experiments in science or discoveries look like accidents, but they're only accidents in the sense that we were trying to find something else, and then we realized that what we had was better for a different application. Graphene is a single-layer carbon. It's one of the strongest materials ever known, and it's completely flexible. The discoverers of graphene won the Nobel Prize in 2010. However, the method they used to make it, which was taking graphite and peeling it with Scotch tape, is not practical. So we set out to find a better method. We start with graphite oxide, which is a water-dispersible material. We then coat it onto sheets of plastic. We hit it with a light from a laser. Deoxygenates, it turns it into graphene.
So it felt very exciting because we made all organic graphene in a very simple process using a consumer-grade DVD drive that you can find everywhere.
But the real discovery was yet to come. I think the eureka moment that you're looking for was not exactly that. The real exciting discovery came when Maher dragged me into the lab, and he said, take a look at this. And he just took a light bulb and he just turned it on with this little piece of graphene. But the amazing thing is, it doesn't stop working. After charging for 2 or 3 seconds, he ran this light for over 5 minutes. I thought we have something very important. I thought the world changed at that point.
Okay, let's talk about the future.
Batteries have a bad reputation, but what we're working on are supercapacitors. And supercapacitors you can think of as a charge storage device like a battery, except it charges and discharges 100 to 1,000 times faster. A battery stores a fair amount of charge, but it charges and discharges slowly. A capacitor puts out a high output, but it doesn't store much charge. So like the flash to a camera. A supercapacitor is one which combines the best attributes of both. If you think about all the electronic devices you have, right now, every time you need one, you realize, oh, I forgot to charge it up. But imagine if you could take that same device, plug it in the wall for 30 seconds or a minute, and be ready to go. Life would be very different. And eventually we'll get to things like electric vehicles. Now you pull into a gas station, well, you'd pull into a charging station, and within a minute it would charge up your car. If you think of batteries, batteries are all composed of a lot of metals. Often they're toxic metals. And so in fact, you're not allowed to throw a battery away. But if you had something that's carbon-based, it wouldn't matter. Carbon-based, you could put it in your compost bin and use it to grow vegetables. When I was a kid, I wanted to be a scientist. And so my goal has always been to develop something that will change people's lives.
So this film was made by a professional videographer for a contest for the Sundance Film Festival last year. And when he made the top 20 finalists, he told me that we should get ready to go to Sundance. But unfortunately, we didn't win. However, when the movie was released to the internet, it went viral. It's probably one of the most watched science videos. Over 2 million people downloaded it. And with that, let me thank all the people who made this possible, which is very hard to do. But the first thing I want to do is thank the wonderful colleagues I've had at UCLA. And I sat down and I looked at how many of my colleagues have I written papers with. And there are actually 36 colleagues, and you can see them all here. And by the way, if your name's not on this list and you'd like to be, just see me after the seminar. I also want to thank, we have some very generous supporters, and I want to especially mention two because they have been great supporters for the Department of Chemistry and Biochemistry as well as my own lab, and that's Ray and Dorothy Wilson and George and Jerry Gregory. And then there's all the funding agencies. We just put their symbols here, but they've been an integral part of our ability to get things done. But the real thing is, I get the pleasure of standing up here and talking, but the people who go in every day and actually do the experiments and make the discoveries, those are my graduate students, postdocs, and undergraduates, and visiting professors. And so I would especially like to thank them. I have one more thank you, and that is UCLA has been a wonderful place to do research, as I think we all know. And one of the crown jewels here is the California Nanosystems Institute. And it has the high-powered microscopes, it has the professional staff that enable us to see things on the nanoscale and to do, a great deal of what I talked about today has been making new materials, and they work because of nano. And so I'm very grateful for the support for this institute. And with that, I want to thank you for coming. I want to thank you for your attention, and I'm very happy to answer questions.
There will be people, sorry. There are people in the audience who will be able to hand you a microphone if you have questions. So if you raise your hand, we will have somebody with a microphone come to you so you can ask the question. Or if you want to volunteer to be one of the co-authors with Professor P, you can do that as well.
Yes, hi. I was just wondering about the Superhard material, the tungsten tetraboride. Is that considered a what do you call it, diamond, synthetic diamond material?
So tungsten tetraboride is a material that is hard enough to scratch diamond, but it's not a synthetic diamond is usually some form of carbon that's made artificially in the lab. So in fact, about 10% of the diamond in the world is actually made in the laboratory. Actually, most of the diamond that's used is actually made in the laboratory, although gemstones are more often made, are mined. But the material that we're making, it's clearly a synthetic material. It's not particularly expensive, and it's extremely hard. But what we do is we're working on the fracture toughness of the material. This is true of all very hard materials. They can be somewhat brittle. And so if you use tungsten carbide, which is really probably our real competition, that's all your drill bits and all your cutting tools all have tungsten carbide in them. And what they do is they put another agent in, they reduce the hardness a little, but they increase the fracture toughness. So that's what we're doing to make improved materials. And so I'm hopeful those experiments are going well. You saw we already have been able to make a cutting tool. And so I'm hoping someday that these materials start replacing some of the current materials. Because a lot of the materials like tungsten carbide wear out very quickly. Others like diamond are just very expensive to make. And the same with cubic boron nitride, which is a diamond replacement.
What are the current challenges and prospects for moving supercapacitors into applications that we currently use batteries for?
So that's a really good question. So supercapacitors, I have a whole series of slides on what they can be used for, but let me give you some of the highlights. So currently, carbon-based supercapacitors are used for electric buses in China. And the idea is if you don't have a lot of infrastructure, don't want to put it in, you just make a charging station, the bus stop, every 5 or 10 miles. And as people get on and off the bus gets charged. So you can do that within a minute to 2 minutes. So there's a promise for using them that way. The real question is, could you stick them into your cell phone? And could you charge your cell phone in 30 seconds or less? And that is a problem that we're actually working on in the lab. In order to do that, we have the power to do that. In other words, we can charge them fast enough. The question is, can we provide enough energy? And in that, we have to combine graphene with some other materials, and that's what we're working on. However, I could today build an external charger. That charger could be charged in 10 seconds. You could put your cell phone in it, you could stick it in your pocket, and it'll trickle charge your cell phone with that charge. So that's a possibility. There's many other applications. My favorite is there's a revolving door at a train station in Amsterdam that's connected to a supercapacitor. So as people go through the revolving door, it runs the restaurant next door, at least the lights. Yes, so we can all be involved with supercapacitors. But there's great promise for portable electronics, for even storing solar energy. And sometimes I joke, you know, if the worst problem you have is that if you're driving from Southern California to Northern California in your electric Tesla, and you have to stop for lunch for 2 hours, well, we could probably solve that problem too. So there's a lot of commercial promise with these materials. They just need to be scaled and improved a bit.
The experiment that you showed where some form of graphene or graphite emitted carbon dioxide.
Yes.
Is there anything reversible about that so that you could absorb carbon dioxide from the atmosphere?
Yes. That's a very good question. It would be very nice to get rid of carbon dioxide, which is the greenhouse gas. But no, this is a very irreversible process. We're using the carbon dioxide to make the expanded lattice. In fact, I can tell you that the surface area of graphene is 2,630 meters squared per gram. And when we do this experiment, we've measured above 1,500 meters squared per gram, which means we've measured beyond what you'd get if you put two sheets together, because that would reduce it by half. So we really have individual sheets separated by these pillars. And so we really have what I like to think of as holy graphite. And so that's why we can make such good charge storage devices. However, capturing CO2 is not one of the things that these are good for. So there are many other ways to do that other people are working on, but it's a good thought. Just these materials aren't meant for that. Oh, very good. If you Google supercapacitor, yes, it's a film by Brian Golden Davis, and it's very easy to find. In fact, if you're interested, KCET, our local public radio station, did an interview with me a few months ago, and it turned out to be the most popular interview that they did all year. It was #1 on the KCET website. I don't know, I haven't seen it myself, but they sent me a thing. If you just go to KCET, I don't know, and just put in my last name, and it should probably pop up. Yeah, we were actually, with that video, my students tell me we were on the top of the Reddit website for a week, which apparently tracks videos, and that, I don't know what that means, but they said that's a good thing. And there's a site that has the most popular videos or short videos of 2013, and we were like #3. And, you know, if you look at the top 10, they're all about famous people or, you know, singers or people doing crazy things, and there's a science video. So it's kind of, it's interesting. And I should tell you that a lot of people have gotten interested in this. The first few high school students that emailed me and say, Professor Kainer, I want to do this for my science project. And I said, I don't think you want to do this for your science project because, yes, graphite oxide's cheap, but we make it in the lab. And if you buy it commercially, it's expensive, and, you know, there's going to be all these problems. And then finally a high school student wrote to me and said, well, it worked, so here it is. And 3 weeks ago, I had a homeschool network email me, and they said, we want to do this for our grade school project or something. And I'm like, and then they, you know, I gave them some advice, and then they emailed me back and they said they did the laser scribing, they put the electrodes together, but they can't get any output current. And I wrote back and I said, did you put in an electrolyte? And they said, what's that? And I said, well, just take some acid, and I told them which one and put it in. And they wrote back and they said it works, and they could light something. So I don't understand it, but apparently this is easy enough that high school students or even grade school with some assistance can actually go and do this. So this LightScribe device, many of us who are older have never heard about LightScribe. But if you have kids and you ask your kids, they know all about it. It's a $25 device that you can buy on the internet. And they use the Gillette razor model. Gillette razor model is give away the razors, sell the blades. So they give away the device with all the very sophisticated software that can raster any digital image. And then what they do is they charge for the LightScribe enabled disk. But what we do is we take their disk and we put a piece of plastic on top. We coat it with graphite oxide, we hit it with a laser, convert it to graphene. We peel off that and use that. And then we put a new piece on. And so we're kind of cheap. And I assume that some of the high school students who are doing this too do the same thing. But it's actually possible. It's been very popular on some of these websites. People start. I was getting several emails a day, and I just referred them to our papers because I just couldn't answer all the emails coming in.
Any other questions? If not, first I would like us all to give a hand to Professor Kaner for a wonderful.
Video copies of this program are available for purchase from the UCLA Instructional Media Library. Call toll-free 1-877-958-2200. Additional information about the people, places, and ideas discussed in this program is available at our website,